All right, class, this is the CFU for 10.3, comparing two means. But this is it's a special section because it's dealing with paired data, match paired data. So concept 1, inference for paired data. So check for understanding. Students will be able to perform a significance test about a mean difference. Okay, so let's dive in, right? A study measured how fast subjects could repeatedly push a button when under the effects of caffeine. Subjects were asked to push a button as many times as possible in 2 minutes after consuming a typical amount of caffeine. During another test session, they were asked to push the button after taking a placebo. Now, placebo is kind of tricking the patient to think that they are actually getting the treatment to cure something, right? To impact or to affect illness or disease, but in reality, they are given like a sugar pill or something. That's what hence the name placebo, is to trick the patient to think that they are taking the actual treatment when in fact they are not. And so, because that way, then the effect that really came about from taking the actual treatment to be compared to the placebo to see if there's a difference. Because let's say if you have a patient, right, you've been given a drug to see if it has any reaction, and then you get tested for it, right? And then you take a placebo, and somehow if both readings are the same, that means that the drug is not really effective, right? Or is it? So this is a significance test for it, and that's the reason for placebo, just to see if the drug is indeed effective. So let's continue. The subjects did not know which treatment they were administered each day. So it's kind of like a blind experiment, right? Blind because the subject doesn't know. Now, if the subject doesn't know and the person administering doesn't know what they are actually giving to the patient, it's called a double blind. Only the people, at the real so-called people in charge of the experiment knows. The people giving, like the doctors who give the treatment, and the subject who is receiving the treatment, if those two parties don't know, it's called a double blind. So, and let's continue. And the order of the treatments was randomly assigned. So randomness was indeed applied. The data given in presses per 2 minutes for each treatment follows, given in the table, right? Use a paired T procedure to determine whether or not caffeine results in a higher rate of beats on average per 2 minute period. Now, what makes this experiment interesting is that this is called a match pair. Now, match pair, if you look at the data right now, you have 11 subjects, and one test, one treatment, they are given caffeine, and then you measure the number of presses. Then another day, the same 11 subjects were not given caffeine; they were given a placebo, right? So the subject think that they are given something, but they may not be told. Doesn't really matter. But they do the same treatment again, and they record the same number of presses. So it seems like it's two different population, right? But it's not, because you're talking about the same subject. So it's like a pre-test and post-test, right? It's being done on the same person. So that's called a match pair. right, rather than a two-sample t-test. Right? So we are not doing a two-sample t-test. We're just doing a match pair. So we need to find the difference between the beats caffeine and the beats placebo. So, right, this is what we need to do. Right, so the difference we need to calculate. That's why there's another column. All right, the difference of caffeine beats minus placebo beats, and then if you do the subtraction accordingly, 251 minus 201, and so that's the list of that's the new data, right? The difference between caffeine and placebo. Now, so I want to proceed because I want to go ahead and calculate the mean of the difference, right? So you have 11 set of data, right? The difference of caffeine minus placebo. Now x bar of the mean of the difference is 11.09 and the standard deviation 21.52. And the sample size is 11. So I would like to show you how we get the mean. So first of all, you need to input the difference, the list of the difference between caffeine and placebo, put into a list on your calculator. Okay, so we put that in a list, right? Put the difference, and then you go to stats, edit. Okay, so check it out. So list 1 has all the list of the difference between the caffeine minus placebo. So to find the mean of that list, so you go to stat, calc, 1 var stats, and then see list 1 is there. Frequency list you don't need. And voila, you see that the mean of the list difference is 11.09. Okay, and the standard deviation we pick. Okay, so the mean, right, sample mean of the difference is from this 11 data, from the set of 11 values is 11.09. And here we have two standard deviation for you to pick. One is S of X, and one is sigma X. Sigma is a parameter, refers to the parameter, right, the population. But we need the sample standard deviation, S sample, and so we need to get this S of X. So it's 21.52, and the N is 11. All right, so it's just as what we have written here. X sample mean X bar D equals to 11.9. S of X bar D equals to 21.52, and N of D equals to 11. So state the test, right? State the test. So we will conduct. So what kind of test are we looking at? A paired t-test, right? A paired t-test because it's a match pair. Paired t-test for the true mean difference between the caffeine and placebo, right? Beats per 2 minutes. Now, we also need to specify the significance level, which in this question it wasn't. So if it's not stated, we assume it to be at alpha equals to be 0.05. And so the hypothesis, the null hypothesis, is that the mean difference equals to 0, right? There's no difference between the two, right? The caffeine and the placebo should have no difference. That's what we are assuming. Then the alternate hypothesis is that the mean difference is greater than 0 because the question says we want to determine whether or not caffeine results in a higher rate of beats. So we are assuming, the alternate is that it's greater than 0. Now at this point, we also need to state what mean mu of D means, right? Mu D is the true mean difference between the beats from caffeine and the beats from placebo for the subjects. Okay. So, state plan. This is the plan part. So the conditions, all right? First conditions, random. And we were told that the treatments were randomly assigned. Woohoo! SRS, simple random sample. Second condition, the large count, which is also the normality conditions. So we do not, unfortunately, we do not have more than 30 subjects. We only have 11. Now, when that happens, right, we really need to check whether the data, if there's any outliers or strong skewness, because, we need more data, but we only have 11. So there are a few ways we can go about trying to see if to look at the skewness, to check the skewness, and to look for outliers. So the thing that I want to show you is that if you can create a box plot, and we do that by doing this. So you go to second stat plot and turn on the very first one, and you need to turn it on. And then, so you see X is L1, but there are 6 things for you to choose. The first one that's blinking is a scatter plot. Second one is a line graph. We're not using that. The third one is a histogram. Now you can actually look at the histogram to see what does it look like. So let's see what it looks like. So zoom 9. Okay, the histogram doesn't. I know there's nothing in here, and there's 1 in here, so it looks like it's a bit skewed, but it's still relatively okay. It's not too bad. Maybe we can look at another one, right? Histogram. So let's look at the box plot with outliers to see if there are any outliers, right? L1. Okay, so everything is zoom 9. No outliers, right? So it may look slightly skewed, right? May look slightly skewed to the left, but I'm not too concerned. So there's another thing that you can do. So second stat plot, and this one is actually pretty interesting. So if you go down to the 6 options you have, if you go to the very last one, and that last one, it's called a normal probability plot. So let me show you what it looks like first. Zoom 9. So if you look at the data, now it looks fairly linear, right? Now when the data looks linear, when the pattern looks roughly linear, you can say that the sampling distribution is approximately normal. Okay? So only when the pattern looks linear in the normal probability plot. So let's go back to... Okay, so let's continue. So a box plot of the differences suggests no outliers, right? I've just showed you. Okay, and then the normal probability plot appears or displays a roughly linear pattern. And that goes to show that the sampling distribution, right, is approximately normal. So next condition, the 10% rule, the 10% rule. So it's reasonable to assume that there are more than, so you take the sample size, which is 11, multiply by 10. So there are more than 110 subjects in the population. Right. So in the do part, we want to find the T statistics, and that is equals to the sample mean X bar D minus mu D, right, divided by S of X bar D divided by square root of N of D, right, the sample size of the difference, which in this case is 11. So if you plug everything in, So it's 11.09 minus 0 because that's what we assume, right? The mean, the true mean difference is equals to 0. Then divided by 21.52, that whole thing is divided by square root of 11, and that comes up to 1.709. I always like to graph, right? So draw a normal curve, which is 0 in the middle, and show where 1.709 is. Now, according to our alternate hypothesis, we are trying to test if the mean difference is greater than 0. So it's to the right. So we are trying to graph to the right, and obviously it's going to positive infinity, and calculator that can't put infinity, and we put a very, very big number. So since this is a t-distribution, we need to use, to calculate the p-value, we need to use t-CDF. And there are three things. It's the lower, upper, and degrees of freedom. So the lower bound is 1.709, upper bound is 99999, degrees of freedom is 11 minus 1, and that comes up to be about 0.059. So that is greater than alpha of 0.05. So to conclude, right, since p-value of 0.059 is greater than the alpha value of 0.05, we fail to reject H0. That just means we do not have sufficient or convincing evidence to suggest that the caffeine results in a higher beats per 2 minutes than the placebo. All right, so now there's a calculator function that I want to introduce. So you go to stat, test, t-test, and this time we're going to use the data. So I'm just going to go to the calculator function, and so if I go to stat, edit, I just want to check if my data is in list one. It is. So if I go to stat and go to tests, I want to go to a t-test, right? So we're not using two sample t-tests. We're using one t-test because we have just calculated our data is the difference, right, between the between the caffeine and the placebo. So t-test, and we're not using stat. We're using data, right? And the data is already in list one, right here. So what was our mean? Our mean is 0. Okay, all right, and L1 and frequency, all those, let's go down. Okay, we need to pick what the alternate hypothesis. Our alternate hypothesis is greater than 0, right? Greater than 0. And then let's go to calculate. All right, voila. So the t statistics is 1.709. The p-value is 0.0591, right? And then look at all that values. So let's scroll down and see if we actually have anything. Oh, okay, there's nothing there. Okay, so apparently everything is there. All right. So let's go back to, all right, so you need to make sure you put down the t statistics, which is 1.709, and the p-value is 0.0591. And this, we actually do not need to put the degrees of freedom. So those are the only two things we need, right, when we're using a calculator. Right, thank you very much. If you have any questions, let me know. Thank you. Bye-bye.